Welcome. Today is going to be the first day we spend on section 5.8. This is actually the last section in the chapter. We're going to be talking about how to find roots of polynomials again, which we've been doing quite a bit of. We've been factoring the polynomials, which is also like finding the roots, because if you set each factor equal to 0 and solve for x, that gives you the root. They might give us 2x to the fourth plus 7x cubed minus 6x squared plus x. That's a fourth power function. Hopefully you can see that you can factor an x out of each term. So when we go to finally factor f of x, if you factor an x out of each term, you get something that looks more like this. And that means, since you've factored an x out, that one of the roots will have to be 0. Because if you set this first x factor equal to 0, you get x equals 0 for a root. But we still have this third power function left over to deal with. We can try factoring this further, but if you group it, you're going to get different things in each set of parentheses. You can't unfoil it, and it's not a difference of squares, it's not a difference of cubes, it's not a sum of cubes. There's just too many terms for all that. So in the past what's happened is they say, okay, well, I'll tell you what, I'll give you one of the roots. They gave us a hint. And then we could divide this third power function by whatever factor they gave us and get the answer down to a depressed polynomial second power function, and then we could maybe unfoil it from there. But today, we're going to have to figure that out on our own. And we'll talk about how to do that in a little bit. First, though, let's take a review, or let's look at a review of Descartes' rule of signs. From Descartes' rule of signs, and I'm going to look at the depressed polynomial here, because I know one of the roots is 0. I'm going to look at the remaining polynomial to figure out what its roots are, because the roots of this thing will also be roots of the parent polynomial that we started out with. Descartes' rule of signs, if we look at this, there's no sign change until you get, oh, there's one. There's a sign change from the 7 to the negative 6, and there's another sign change from the negative 6 to the positive 1. That's a total of 2 sign changes in the terms of the function. And what Descartes' rule of signs says is that means there's either 2 or positive zeros, 2 or 0 positive roots for the function. If you plug negative x in every time there's an x into this function, the 2x cubed will switch to a negative 2x cubed, because an odd power with a negative plugged in will change signs. If you plug a negative in for an even power, the sign will stay the same. If you plug a negative in for a first power, the sign will change to a positive in this case, and your constant will never change signs. That's what makes it a constant. So in the new function, we have one sign change here, and then that's it. So there's only one sign change in f of negative x. Descartes' rule of signs says that means there's only one negative root for the function. Now, what we really haven't talked about is imaginary roots. So you can use Descartes' rule to kind of help you figure out if there are any imaginary roots and how many there would be. So here was our original function. We know that it's a degree of 4 because the highest power is 4, which means there should be 4 total roots. We already said one of them is 0 because you can factor that x out. And then there's either 2 or 0 positive roots. We found that from Descartes' rule. And there's one negative root. We also found that from Descartes' rule. Now, if you do the math on this, if there's 4 total roots, one of them's already accounted for, it's 0. Let's pretend for a minute there's 2 positive roots and 1 negative root. So we've got a 0 root, 2 positives, and a negative. That is a total of 4 roots. So one possible combination of roots would be one of them 0, 2 of them are positive, and one of them's negative. Another possibility would be, with our four total roots, 1, 0, then none of them are positive. Because we got to look at that possibility. That's what or means. Look at one case or the other. So if one of them's 0, there are no positive roots, and then one of them's negative. If that's the case, one of them's 0, none of them are positive, and one of them's negative, that only gives you a total of 1, 2 roots. And if that's the case, there's still got to be a total of 4 roots. The other 2 roots must be imaginary. And those are really the only 2 possibilities here, because there is only one sign that has more than one possibility. We've listed every single possible thing that could happen for our roots on this function. So again, here's our original function. Here's our depressed function when we factored out the x. We know one of the roots is 0. We've got to go and find another root so that we can divide this third power by that factor and get it down to a second power. Second power we can handle. We can either factor second power or at least plug the values into the quadratic formula. But we got to get down to a second power. So there's something called rational roots theorem that says you can make a list of possible numbers that would be rational roots for this function. It doesn't guarantee you what the numbers are, but if you're just going to guess and check like 1 and 2 and 3, this will narrow down your possibilities. So rational roots theorem, it's a little wordy, it's not so bad once you get to know it. Let's first look at the words. If a polynomial function is going to have any rational roots, so we hope this does, so we can divide it by that root's factor. If that's going to have any rational roots, the root will have to be one of the factors of the constant term, which is your plus 1 here, over one of the factors of your lead coefficient, which is 2 here. Constant term is the one we typically see at the end. Lead coefficient is the one we typically see at the beginning, the one next to the greatest power. So what that means for us, for this function, we already know one of the roots is 0. The constant term here is 1. And its factors are, I'm going to include both the positive and the negative possibilities, but the only factor of 1 is 1. We're going to include both positive and negative possibilities here. So plus and minus 1 are the factors of the last term. The lead coefficient is 2, and its only factors are 1 and 2. So we're going to make a list of numbers to try as roots that are all the factors of this thing over all the factors of this thing. So doing that here, we'd have one possibility would be 1 over 1, because 1 is a factor for everything. And another possibility would be 1 over 2. So you make a bunch of fractions to try. The tops of each fraction will be factors of the last term, and the bottoms of the fractions will be factors of the first term. I'll say that again. The tops of the fractions will be factors of the last term. The bottoms of the fractions will be factors of the first term. For us, all the factors of the last term are 1, so all our fractions have numerators of 1. 1 over 1 and 1 over 2. Those are all of our possibilities. I'm going to put a plus minus on each one. If you simplify, 1 over 1 is simply 1. 1 over 2 is 1 over 2. These are the numbers I'm going to try to find out if they're roots. If there is a rational root to be found, it's one of these numbers. So I'm going to plug them each into this polynomial and see if I get a 0. So these are the numbers. I've transferred them over here. These are the numbers I want to try. I'm going to set up a synthetic division problem. I'm going to plug in +1 first here. And my coefficients coming out of here are 2, 7, -6, and 1. If I run synthetic on this, I'm not feeling good about this number. I don't get 0 at the end. Whoops. I don't get 0 at the end, so +1 does not work. I'm going to try -1. Oh boy, that doesn't work either. Okay. I'm going to try 1/2. There we go. So 1/2 is a root. That means x minus 1/2 is a factor. My depressed polynomial would be 2x squared now. I started out as a third power. I divided it by a first power because I use synthetic division. That means my answer should have a degree of 2. So I got 2x squared plus 8x minus 2. I'm going to factor a 2 out of that. So my depressed polynomial now looks like this. And I can try to factor this second power even further, but in truth, try as you may, it will not unfoil. So if we're going to list f of x as being factored, here's what we'd have. We'd have the x that we pulled out right away. We'd have the 2 that we factored out. We'd have x minus 1/2, because 1/2 was a root. That means x minus 1/2 will be a factor. And then we'd have the x squared plus 4x minus 1 that simply won't unfoil for us. Maybe an even tidier way of writing this would be to put the, to go ahead and see there how there's a 2 out here and a 1/2 inside. You could actually distribute this 2 in and get rid of the half. If you do that, you'd get just a -1 in here. This would really be the ideal way to list your answer. Now if they wanted the roots, that's very related to this, we just set each factor in f of x equal to 0. So if the first factor is 0, that means x would be 0. If the 2x minus 1 equals 0, that means x would be 1/2. And then to get x squared plus 4x minus 1 equals 0, it won't factor, so we'd have to use quadratic formula for the last part. All right, so we're going to run quadratic formula on this x squared plus 4x minus 1. On that thing. Those are the last 2 roots that we don't have. If I use quadratic formula, my negative b becomes a -4 plus minus square root. B squared becomes 4 squared minus 4ac is 4 times a is 1. That's the number, the lead coefficient. C is -1. Over 2a is 2 times, again, our lead coefficient is 1. And it's just a matter of simplifying all this. the 4 squared becomes a 16. And then there's a -4 and later on a -1 getting multiplied on. That'll change your sign here to a positive. And then, of course, 4 times 1 times 1 is 4. And on the bottom, 2 times 1 is 2. You then simplify the 16 plus 4 to a 20. 20 is not a perfect square, but 4 is, and 4 goes into it. So we split up that square root 20, like that. And square root of 4 simplifies to just plain old 2. So we got that going for us. And finally, there's a 4 on the outside here, a 2 on the outside here. They both divide by 2 in the bottom, so we're not going to have a fraction in our answer anymore. Our simplified answer would look like that. -2 plus minus the square root of 5. That's actually 2 roots. The plus and minus sign gives you 2 different values, which means those are the last 2 roots in the problem. So going back to the whole what are the roots question, we'd have x is -2 plus minus square root 5. You'll forgive my typing instead of symbols here. But if they'd asked us to find the roots, we now have 1, 2, 3, and 4, which is good because there was a 4th power function. The -2 plus the square root of 5 would be just, I think, just barely positive. And the 1/2 is also positive. When we go back to the beginning here, we said there could be 2 positive roots, which we found. There was also the -2 minus the square root of 5 would give you a negative number. So there's 1 negative root here. And if you go back to the beginning, oops, we said there would be 1 negative root. So this all does check out. All right, this problem, this example, it says to just find the roots of the function. I'm going to take you through all the steps kind of leading up to it, in addition to some you really wouldn't have to do just to find the roots, because they are going to ask you to do that on the homework tonight. On every problem, they're going to want you to find all the combinations of positive, negative, and imaginary roots. So let's start with that. This function, just looking at it through Descartes rule eyes here, has 1, 2, and then 3 sign changes. So there are going to be 3 or possibly 1 positive roots. We also need an expression for f of -x so that we can figure out how many possible negative roots there could be. And in doing so, the odd power here, when you plug a negative in, it will switch signs, so that'll become a negative. The even power, even when you plug a negative in, it will not change signs, so it stays positive, or it stays negative, I mean. This is an odd power, so plugging a -x in for it will switch the sign, in this case to a negative, and the constant will never switch signs. And you'll see there are no sign changes. All the terms in f of -x are negative, so there will be no negative roots here. For the possible imaginary roots, if you consider there could be 3 positive roots and no negative roots, that combination would already give you 3 roots. There would be no roots left over to be imaginary. So it is possible that you have no imaginary roots for this. Another possibility would be you'd have 1 positive root along with your 0 negative roots. That would give you a total of 1 root so far. There's supposed to be 3. That means we're too short, so another possibility would be that there would be 2 imaginary roots. So you could have 3 or 1 positive, there are 0 negative, and then you could have 0 or 2 that are imaginary. Next, we'll need to create a list of numbers that could be roots. So we're going to come up with actual number answers here, things that could be roots for this function. We're going to use the rational roots theorem to help us. Remember, rational roots theorem says you want to look at the last coefficient, in this case that's -10, its factors, are, the factors of 10 are plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. Our lead coefficient is 1. Its only factor is 1. I know it's plus and minus 1, but I've already got all my pluses and minuses here. I don't need to write it twice. So to make a list of numbers that could be factors for f, you'd take all the numbers in the last number, all the numbers that are factors for the last term, so this list. These will be your numerators in each of your possible answers. And in this case, just the 1 would be the denominator for each. Now this is kind of nice. When they give you a lead coefficient of 1, all your answers will be over 1, which is to say they'll be integers. They're not going to be fractional numbers. So really this list by itself would be all the possible roots for f, the rational roots. Now a second ago, Descartes' rule told us that there are no negative roots. So quite frankly, I'm not going to plug in any negative numbers here. I'm just going to plug in the 1, the 2, the 5, or the 10 and see which one gives me a 0 when I run a synthetic substitution on it. So I'm going to plug 1 in first. If I bring down a 1 here, I don't think this is going to work out. Nope, you do not get 0 for your remainder. So I'm going to try plugging in something else. I'm going to try a 2. Hey, it works. All right, so 2 is a root. Another way of putting that would be x minus 2 is a factor. To get the other two factors, I'm going to take the original function and divide it by this, which I guess I've kind of already done here with my synthetic substitution. It's also synthetic division. I get x squared, 1x squared that is, minus 4x, and then plus 5 with no remainder. If I factor this, I think this one will actually factor. The x squared gives you x times x. The 5 would have to come from, oh wait, this doesn't factor. Because our signs have to be the same. So I'd need a minus 5 times a negative 1, and that would not combine to give me a negative 4 in the middle. That would give me negative 5 minus 1. That would give me negative 6. So this is not factored. In order to get my roots, I'd have to use quadratic formula again. Quadratic formula, I'm just going to kind of show you the work here, would give you something like this. You can kind of process this on your own speed if you want to hit pause. But ultimately, you're going to get a negative inside a square root. Hopefully you remember how to deal with that. There's going to be an imaginary answer. Square root of positive 4 would give me plain old 2. So the square root of negative 4 will give me 2i. And once again, we see both the terms up in the numerator will divide by that 2 in the denominator. And as a result, you get 2 plus and minus I for your other two roots. So we got 2 for our real root, 2 plus I, and 2 minus I for imaginary roots, and those are the 3 roots we're supposed to find. So the 2 examples we looked at today are like the longest kind of problems you'd see on the homework. The first several, I believe, are just list the number of possible positive roots, negative roots, and imaginary roots. The last handful, you actually have to go and find the roots as well.